Well, Dr. Clark here again for Fish and Wildlife lecture. This time we are looking at sex and fecundity. Sex in general, we're actually looking at what's the difference between the two genders. In other words, in fish and wildlife management, it's often of interest to the manager how many males you have in a population versus how many females you have in a population. This is a sex ratio, okay, made famous by Fisher. But at any rate, the ratio of sex for most organisms is kind of a 1-to-1 when they're first um, born, okay, or hatch, or whatever the organism is. It's a 1-to-1 ratio, males to females. Now, there are lots of organisms that can skew this ratio tremendously. Okay, so turtles, which are temperature determinant, some turtles, which are temperature determinant sex ratios, they can be like 90-10 males to females, or flip it 10 males to 90 females. They have the capability of doing that because the sex of the individual offspring is determined by the temperature of the environment. There are lots of other ways at which organisms have the capability of skewing their sex ratios. Some organisms, if they give birth to a male and there's too many males, they'll just consume the male, or chase it off, or there is a lot of different ways to do that. But for the most part, for the organisms that we're most interested in, that would be organisms that we consider game. The sex ratio is going to be somewhere around 1-to-1. Now, I, I have to preface that with ducks in different regions are not 1-to-1. And so I have to kind of preface that. That is a game animal that often will not have a 1-to-1 ratio. Normally it's skewed towards males. And there are reasons for skewing one way or the other. Often it's because the organism having a certain sex or being a certain gender, you have a disadvantage in the environment. Okay? So if you're brightly colored and you're a male, then you're small, you're more likely to be consumed, okay, by a predator because you're easier to pick out, you don't have camouflage, that kind of thing. So sometimes in birds where you have songbirds or something like that, one individual is really brightly colored and the other individual, typically female, is not brightly colored and matches the environment, you might see a skewed ratio towards the males, to kind of keep more males in the population. Okay, so at any rate, we're not really going to talk about sex ratio. That's important, but that's really, really simple stuff. Okay, we're going to talk more about, well, how do you determine the sex of the individual? What are the means by which you can determine the sex of the individual? And then we're going to talk about the relationship of fecundity, or the relationship of eggs and how many eggs are produced, or what's the success of reproduction, okay? And how do we calculate that success? Okay, so most of you are fairly familiar with what's called sexual dimorphism. Okay? And there's really two versions of sexual dimorphism. Sexual dimorphism in itself, and we'll come back and we'll talk more about that, is often that one organism is got some kind of morphological feature that differs than the other gender. Okay, in the case of elk and deer and things like that, the male has antlers, the female does not. Okay, that's sexual dimorphism. Okay, there's another variety of sexual dimorphism, which we call sexual chromatism or chromatism, okay, which indicates color. Okay, so if you look at the sage grouse, you can see that not only are they sexually dimorphic in morphology, okay, so they have tail feathers that are different, they have, head feathers that are different. Okay? They're also sexually chromatic in the sense that they have a different color pattern than the female. Okay, so let's look at some examples of that again. So again, sexual dimorphism is a difference in form or shape due to the sex of the individual. And like we said before, or like I said before, this is very common in game animals that we have hunting seasons for. Deer, elk, antelope, even moose, um, just lots and lots of organisms that we hunt. Okay, most of the game birds, you can tell the difference between males and females. Some of them are dimorphic, in the sense that they have different feathers than the females. Like grouse, they have different tail feathers. Pheasants have different tail feathers, or there's sexual dichromatism or chromatism, referring to the actual color difference between the two. So here you can see these are collared lizards. You can see that there's a difference. This is the male, this is the female. Now both of them are colorful, but the male has a different color pattern than the female. Okay? In some organisms, it's both dimorphism and dichromatism, chromatism, okay, in the sense that they differ in shape and they differ in color. So you can have things like a knoll lizards, which will have a colored flap called a dewlap, the skin flap on their throat. Okay, that's dimorphism and dichromatism because the color differs and there's a morphological difference in shape. Okay, so for a lot of organisms, that's really simple stuff. I mean, most people can just go out and they can look at a population of deer and they can say, all right, there are 5 males, there are 15 females. Got it. Okay, you can move to the next one. Okay, on and on and on and on. Now, for some organisms, though, there is no dimorphism or dichromatism. For some, you have to do different ways. You actually have to sex the organism. Okay, so for some waterfowl species, you need to do what's called a cloacal probe. And this is also true of reptiles, and in some cases, it depends on the reptile, but lizards and snakes have what we call a hemipenis, which is a split penis. And so you can do a cloacal probe and find out whether it's a male or a female. I'll show you here in a second. Okay. So here you can see this is a Canada goose, okay, Brant canadensis. Okay, and we're going to put a band on this individual. But first, we're trying to figure out, is this a male or is this a female? If you haven't experienced much when it comes to geese, but geese are not sexually dimorphic. You cannot tell the difference between a male and a female goose. Now, in some cases, the female might be a little bit larger, but that doesn't really work when you're trying to do a population analysis, when you're trying to look at how many males and females are out there. The best way to do this is to do what's called a cloacal probe. In the case of waterfowl, it doesn't actually involve a probe, but it's actually involving you inverting the penis. Okay, and so here you can see in this kind of sketch here, this is the cloaca. Okay, if you invert it, if you kind of push, you can get the penis to come out of the cloaca, obviously indicating that this is a male. Okay, in the case of cloacal probing of reptiles. So snakes and lizards mainly, they have two peni or two penises called hemipenes. You can see them here. They've been inverted. Now, in some cases, you can invert these, but it's much easier to actually just take a little probe and run it down the cloaca so the hemipenes are encased on each side kind of their tail, the upper portion of their tail. So you can insert a probe into the cloaca, and if it goes into the cloaca down into kind of one of these sacs that holds the hemipene, then you know it's a male. If the probe doesn't enter, it doesn't move down into the sac, then you know that it's a female. So simple things like cloacal probes, and maybe they don't seem simple to you, but simple to individuals who do it on an everyday basis. That's one way to do it. Okay. The other way is to examine behavior. So in some things, there are behavioral cues that indicate whether it's a male or female. Take, for example, frogs. There are a lot of frogs that are not sexually dimorphic, but females don't call. Only males call. And so if you find a male that's or an organism that's calling, okay, you would know therefore that it's a male. Okay, there are lots of other organisms, okay, that are not sexually dimorphic, but maybe they do a dance of some sort. Okay, lots of insects that are not sexually dimorphic, but the insect calls, and only the male would have that calling capability, or the male might flutter its wings, or the male might do a dance, these different things. Most of the time, it's males who are trying to attract females through behavioral cues. Sometimes that's not the case, but majority of the time it's the male. And then, of course, there's dissection. This clearly would mean that you have to kill the organism. But in the case of some species, it's really the only way to tell the difference between males and females. And if that's part of, the management plan is to decide, okay, well, are the ratios in this population 1-to-1, or is it, more males than females, etc. You can do dissection. So most fish are not sexually dimorphic. Most game fish, I should say, are not sexually dimorphic, and so the way at which you would get that kind of data is you'd have to do a dissection of a certain number of fish. Okay? Now, in some cases, they are sexually dimorphic because maybe females are bigger than males, maybe females weigh more than males. It depends a lot on the fecundity of the individual. Okay? Are females reproducing, are producing a lot more eggs, a lot more mass to their gonads than the males? In that case, you might have a difference in size or a difference in mass of individuals that you could pick up knowing enough about that group. Now, it still would probably have to involve some dissection because you have to make sure that you're correct. And really the only way to make sure you're correct in the case of, most fish is to actually do the dissection. Okay. All right, so let's look at some other things that are important. Sex ratio is important, but then what do you do with that data, okay, outside of sex ratio? Okay, yes, knowing males and the ratio of males to females is great. Okay, then you can set your limits on your hunting season. Okay, we need to take more females out of the population. There's too many females. Okay, so maybe we need to open a doe season. Or maybe there's not enough females, not enough reproduction, so maybe it's only, bucks only kind of thing. So this kind of information, the sex ratio information, really can can kind of gear you towards that. Okay. Same thing with birds. All right. You can't take any hens. Only, drakes only. Okay. So if we're talking about ducks or something like that, male pheasants only. Okay. That's fairly common most every hunting season. If you're hunting pheasants, it's males only. And other grouse and things like that, it depends on the season whether you could tell the difference between males and females, etc., outside of the breeding season. Okay. But what a lot of managers are interested in is also that piece of sex or the piece of gender that indicates what's the next population going to be. How many offspring are going to be added into the environment? And you get at that by looking at things like gonad mass. Well, in the case of organisms that produce large amounts of offspring. And so mainly I'm going to talk about this from a fisheries industry. Because as far as a big game industry goes, gonad mass is, it might be important to know the mass of the organism that's, going to give birth, because that will often determine how much energy is going into that offspring, how much milk production, that kind of stuff. Gonad mass is more important for things that are not tied to a placenta, but rather are offloading a massive number of eggs. Those eggs are going to hatch, and that's going to be your next generation's, cohort. Okay, so fisheries industry often look at gonad mass. Okay, now it's not just examining females. Now, often we think, okay, well, females is the reproduction output that's going to be put into the next generation. This is very true. But if you do not have enough males and enough sperm, okay, from those males, then it doesn't matter how many eggs that a female produces. If you can't fertilize those eggs, then you're in trouble from the standpoint of what's the next cohort going to look like. So male gonad mass is kind of important. It also tells you a lot about what's going on with the male's growth rate, okay, or even the male's ability to compete for a female. Okay, so it really depends on the organism that is of interest. Like I said before, most fish are not sexually dimorphic or sexually chromatic. So therefore, most fish are about the same size, males to females. Now, if females are bigger, then you know that that's because they are gearing up, and the bigger the female, the more eggs they can hold, typically in the case of fish. Okay? But if the size of the two is nearly the same, okay, then you have to examine, well, what are males doing with all the extra energy? Realizing that sperm is very cheap compared to eggs. Eggs are expensive, energetically speaking. Sperm is cheap, energetically speaking. So if the two organisms are about the same size and males are not greatly bigger than females, which sometimes is the case, the male is much larger than the female, okay, that means, okay, well, it's taking that extra energy that it saves on gonads and it's applying to growth. Okay? So if the two are the same, though, then you know that males must be doing something with their energy. In the case of maybe behaviorally, they're expending their energy. So maybe they're chasing females, maybe they're holding nests, maybe they're fighting with other males. Something's going on to expend that energy that they're saving on gonads. Okay? And that's important to know, especially if you're managing things like non-game species, okay? Species that might be threatened, endangered, or species of concern. If that's your management job, then you need to know more about that organism from the standpoint of what's the differences between males and females. All right, so fecundity, or F, is the number of eggs produced, okay, in relationship to kind of the mass of the organism. That's often what we use fecundity for, is, okay, well, how many eggs are produced in relationship to the female size? Fecundity itself is just the number of eggs produced, and most of the time we get at this by a gravimetric method, meaning that you're not actually counting the total number of eggs an organism is producing, okay? And if you ever calculate a fecundity, you'll appreciate this method, because counting out 500,000 trout eggs, it's just not time efficient. So instead, what you do is you weigh out the gonad's mass, okay, and then you figure out the mass of a single egg. And that'll give you the fecundity. Now, often the eggs are so small that you're actually not counting a single egg, but maybe you count out 100 eggs, or 50, or 10, or 20, okay? Get the mass of 20 eggs, find out what the mass of a single egg is, gonad mass, and that'll give you the number of eggs that a female produced. Okay? It's a pretty simple process. Well, then what do you do with it? Well, now, like I said before, maybe you're interested in, well, how does the fecundity relate to the size of the organism? How does the gonads, maybe we're looking at males now, how does that relate to the size of the organism? Okay? And maybe you're examining two separate populations, maybe two separate streams, or maybe you're examining, a population of fish in a marine environment. Maybe they're in an estuary versus open ocean. Maybe they're in a marine habitat protection area. So you might just be, examining differences in populations. One way to do that is to look at what we call a gonadal index, or GI. And that is to examine the relationship of the mass of the gonads to the length of the organism. Okay? And so, is an organism that's longer producing more gonadal mass? Okay? And then where does that tailor off? Okay? So what's that relationship? Okay? And that's important to know, mainly because what can occur, and often does occur, okay, is organisms, especially in things like fish, okay, and aquatic organisms, if the environment's poor, they will push a lot of their energy straight into gonads. Okay? They'll forego growing really big for being able to reproduce now. Okay? A GI index will tell you that. It'll tell you that relationship. Okay? A better index and a more robust index is to actually look at the GSI, or the gonadal somatic index, okay, which is going to look at the actual mass of the organism, not the length of the organism. And so this tells you basically, are organisms that are longer or have more length to them, are they producing a bigger gonad mass? The gonadosomatic index, on the other hand, is basically telling you what's percent of the body mass, what percent of this organism is donated or is gonads. Okay? So what percent of the organism's mass is wrapped up in reproduction purposes, or reproduction parts? By comparing that in different environments, you can definitely get at okay, well, is this environment smaller and reproducing at a much smaller age versus this environment who's waiting and reproducing at a larger egg and can donate a lot more um, body mass to gonads? What is the difference between those two? Okay. So that's kind of how fishery scientists look at fecundity and gonad mass and the information that they can get from that. Okay. Now we're going to switch gears just a little bit and examine how ornithologists or bird biologists examine their reproductive pieces. Okay? And that brings me to another example, another assignment that you're going to do, and that is to be able to estimate nest survival. Okay? We're going to use what we call the Mayfield Nest Survival Estimator, or what's normally just called Mayfield Estimator, okay? Because it was made by an individual who's named Mayfield. But this is going to get at what is the survival rate of a given nest. Okay? So ornithologists, bird biologists are often interested. It's extremely important, probably more important than most organisms, that a bird has a good reproductive event. Now you have to think about this. I understand that mammalogists and big game biologists would probably say, well, it's just important for a deer to give birth to their offspring this year as it would be for a duck to give to have a successful nest. And I would argue that is not true, mainly because a duck's lifespan is shorter than a deer's lifespan. Okay? So the number of reproductive events that a duck has is less than a deer or an elk or an antelope for that matter. The other thing is the migration or amount of migration that, say, a waterfowl does is far larger, far more drastic than, say, a big game animal. So from a survival point of view, nest survival is far more important to birds in a given season than it would be for, most big game animals. Okay? So being able to predict the nest survival is highly important for managers, especially if you're managing for high populations or whatever it might be of a game animal or maybe a non-game animal. Okay? So daily nest survival is the probability that a nest survives from one day to the next. Okay? Important, but more important for most managers is what's the nest survival? What's the probability that this nest or any given nest from that species fledges at least one young? Okay, fledges means the bird hatches, okay, and then leaves the nest as a juvenile organism, okay, and it's no longer cared for by the parent. That's a fledge, okay, and it will depend purely on, well, is this organism precocial or altricial? Okay? And nest survival in its own right differs between those two. But that really comes at what's the period of incubation. Okay, and we'll get to this in a second. Okay, so daily survival important, nest survival more important. Okay, to know that what's the probability or what's the chances that you're going to get a nest that fledges at least one young. Okay. So there are two ways to calculate a Mayfield estimator. Okay? The first one is this equation, 1 minus the total number of failed nests divided by the total number of exposure days. That equals your daily survival probability. Okay? I prefer this equation a little bit more. There's really no difference between the two equations. I just like the way this one's set up a little better. So daily survival probability is equal to the exposure days. This is total number of exposure days minus the failed nest divided by the exposure days. Okay, and we'll come back and I'll talk more and show you an example of what exposure days means. Okay, now what are we really interested in? Not necessarily the daily survival probability, but what's the nest survival probability? So nest survival probability is equal to the daily survival probability, okay, raised to the power of whatever the nesting period is. See, this is where precocial and altricial birds differ. Their nesting periods will often differ. The number of days to fledge will often differ between those two types of birds. Okay? We'll look at that at a later date. All right, so let's do an example. Let's say we have 20 American robin nests that we're monitoring. Okay? And of the 20 American robin nests, 10 of them failed. Okay? The total number of exposure days is 301. Okay? Now, what we're interested in, though, as a manager, is what is the chance that nest number 21 will fledge a single young? Okay? Now, most of you would say, well, that's simple. Okay? 10 failed, 10 didn't fail. It's a 50% chance. Okay? But you're wrong. Okay? It's not a 50% chance. Okay? And that's why the Mayfield estimator was created, because it's actually not 50-50, because it's not dependent on how many failed and how many did not fail. Okay? It's dependent on also how many days. Okay? What was the failure rate? How many exposure days did you have? Are these 10 failures early on, or are these 10 failures really late in the system? Okay? Are they failing when they're in the egg stage because they've been predated as an egg, or are they failing when they've already hatched and the females are not finding enough food, so the babies are starving to death in the nest? There's a very large difference between 10 failed nests that predators ate the eggs versus 10 failed nests that the offspring died of starvation. Okay? And that's where the Mayfield estimate comes in. So I just pulled a hypothetical system up, okay, and I said that here's the 20 nests, okay, and this is how you would set up a Mayfield estimate. Okay, here's your 20 nests, okay, and then on May 1st is when you found every one of those nests. Okay, so 1 here in the box indicates that there was, that organism was in the nest. Okay, so in the case of May 1st, there would have been eggs in the nest. Okay, on May 8th, so I came back a week later, okay, and went through. Now, in some cases, the nest had offspring in it or organism in it. In other cases, it was either destroyed, missing, the organisms were dead, whatever, it failed. Okay, that's a 0. Okay, so knowing that, we can jump over to exposure days. Okay? So in nest number 2, if I jump over to exposure days, you can see that I have a exposure day of 3.5 days. The reason why it's 3.5 days is I found it on the 1st of May. I revisited it on the 8th of May, 7 days later. Okay? I actually do not know when it failed in those 7 days. So what Mayfield suggested is, because you don't know when it failed, it could have failed on the 7th of May, it could have failed on the 2nd of May, because you don't know, you should just divide the 7 days in half, and that's your exposure day, 3.5. Okay? So then if I come down to nest number 3, it survived 7 days, it survived 14 days, but now on the 21st, I didn't see it, okay? Or it was destroyed. Okay? So I have to add 3.5 to the 14, 17.5 exposure days. You do that with all your nests, and you come down and you get a total number of exposure days. In this case, 301, like I said before. Okay, so again, we're not interested in necessarily these nests, okay, unless they haven't fledged young. Now again, we're talking about 21 days. Okay? These nests might not have fledged. These young might still be in their nest. So now we are kind of interested in, if they're still in their nest and they haven't fledged, or they're not about ready to fledge, what's their chances of surviving? Okay? But we also are interested in, well, if we find another nest, nest number 21, okay, or if we have another nest, nest number 21, what's the chances of that fledging a young? Okay? So here we're going to use that equation that, daily nest survival is equal to the number of exposure days minus the number of failed nests divided by the number of exposure days. So here is the daily survival rate, 0.966777. Okay? But again, that's not what we're really interested in. I'm interested in what's the nest survival. Okay? So if we know something about American robins, which in this case, because we're studying them, we're going to know that, we know that their nesting period is about 26 days. 4 days laying, 12 days incubation, 10 days nesting. Okay, so 4 days of laying is basically nest building, that kind of thing, and then drop a single egg each day. That's where that kind of 4 days of laying comes. One egg each day. Most robins drop 4 eggs at a time. Okay? And then they start incubating, 12 incubation days. Okay? And then those offspring, this altricial bird, okay, these offspring are fed for about 10 days as nestlings. Okay? So a total of 26 days. So now, knowing what our daily rate is, now we can find out what our nest survival probability is. If we take 0.966777, raise it 26 days, okay, this is our nest survival probability, 41.5%, not 50%. Okay? It's not a 50-50 chance. Okay? It's actually lower than that. You have about a 41.5% chance that a 21st nest will fledge a young. Okay? So that's how the Mayfield estimator is used, and it's really, really important for ornithologists or bird managers to use this, and they use it quite often to predict, okay, well, what's going to happen to these birds, etc., in a given amount of time. What's the nest chance? Okay, and there are a lot of estimators that are far more robust. Okay, you can use a program called Program Mark, which allows for you to use their program to calculate even a more robust survival rate. That's not just taking into account whether it was it survived. Okay, it's also taking into account what happened to the nest. Is the nest, were the offspring dead? Okay, like on out here on the 21st, these organisms had already hatched. Were there offspring in the nest? Did they starve? What's the condition of the nest? There's other components that can go into these models that can give you a better predictive model. But at any rate, this is a pretty good predictive model telling you that about 41.5% chance that you'll fledge a young if you have another nest. Okay. All right. So with that should help you be able to do the assignment and give you some information about the role that sex, fecundity, and just the ability to predict nest survival plays in fish and wildlife management. Till next time.